release your screen sharing.
Should I end
Stop
my screen?
presenting.
Yeah, stop
Yeah.
sharing.
Hi everyone. Sorry for joining late.
Hi, Anjiang.
Sorry, I just finished the previous session. Sorry.
It's okay, no problem. We still have time. Oh, okay, it's 10 o'clock. All right. We're still missing one presenter, but since time is up now, so we're gonna start the session. Hello, everyone. Um, my name is Seok Won Lee from Aji University in South Korea. I'm the session chair, and it's very nice to with you guys all here virtually. It would have been much nicer if we meet in person. But this session is machine learning for software engineering, and we have 6 papers. And it's a nice combination of journal first papers and technical papers. So very interesting. Um, um, I know you guys all know the order of the presentation. The very first paper is a journal paper, a journal first paper, and the presenter will be Hong Jin Kang. I know you are here, so I think you can start when you're ready.
Okay, let me share my screen. Right, so I'm Hong Jin from Singapore Management University, and then now I'll present our work on active learning of discriminative subgraph patterns for API misuse detection. So the context of our work are on modern software systems, which rely heavily on third-party libraries. And for software systems to interact with these libraries, they do so through the APIs that are exposed by the libraries. However, APIs may have usage constraints associated with them, and the violations of these usage constraints are known as API misuses. And API misuses may lead to bugs and vulnerabilities, and therefore it is important to detect them. Prior work has shown that a promising direction is to mine frequent patterns from projects on GitHub. For example, in this subgraph we see on the right, this graph represents the need for a null check on the return value of map.get. And then after we detect this frequent pattern, we could then detect misusers by looking for deviations from this frequent pattern, or in other words, usages of map without the null check. However, in this paper, we suggest that alone, GitHub would be an unreliable teacher because frequency is not equal to correctness. There are 2 reasons for this. The first reason is that there are many wrong examples on GitHub. For example, it is well known that many users of cryptographic APIs are misusers. And the second reason is that frequent patterns may not represent usage constraints. So in the same example of map.get, on GitHub, we would see a lot of examples that are accompanied by a print line. So developers like to print the return value of map.get to standard output. So if we tried to mine examples from GitHub, we would mine many wrong examples, and we also mine many usage patterns which are not usage constraints. To address these issues, we try to involve a human annotator for supervision, making it a supervised machine learning task. So we would ask a human annotator to label if each example if an example from GitHub is a misuse or is a correct usage. So given that we have graphs that are labeled now, we can then mine discriminative subgraph patterns. So this is in contrast to prior work, which mined frequent patterns. So discriminative subgraph patterns are patterns where their absence or presence would be indicative of a graph's class. In this case, whether it is a misuse or a correct usage. Of course, this requires substantial human effort and would be impractical because we cannot possibly expect a human annotator to label every example on GitHub. And to address this issue, we looked at a field of active learning, which aims to query humans of labels of only informative and representative examples. So here's an intuition of what active learning means in this context, or how we interpreted the principles of active learning. The idea is that we would ask a human annotator to label a small number of usage examples that would tell us enough about some patterns such that we could say a lot about many different examples or graphs on GitHub. So essentially, we construct this logic program and then we query the graphs that the human annotator has to label. And then after we've mined the discriminative subgraph patterns, we would in order to use it in a machine learning classifier, we would have to convert all the test programs in the testing data set into vectors that can be passed to a machine learning classifier. To do so, we would first convert the test program into a graph, and then we enumerate over all the discriminative subgraph patterns to see if the discriminative subgraph matches the program's graph or not. So if it is not a subgraph, then we fill the vector with 0. And if it is a subgraph, then we fill it with 1s. So at the end of this process, we would have a vector of 1s and 0s, and then this can be passed into a machine learning classifier. So in total, we studied 57 APIs from the standard library and also in popular Java libraries. And for each API, we collect from GitHub over 2,300 usage examples. And on average, we had to label about 50 examples in each iteration, in total. And we evaluated our approach on MuleBench, which is a standard API misuse detector benchmark. And we find that, so in this table, the first half of the table shows approaches that only mines examples from within a single project. So the prior work showed that by learning examples from GitHub, we could get a large performance improvement. So the approach was MuleDetect XP, which learns from projects on GitHub. And then our approach ELP improves over MuleDetect XP by making use of active learning and human supervision. So in summary, we have looked at the problem of API misuses, and we have discussed that it's important to detect them. And prior work has shown that finding patterns from projects across GitHub is promising, but we argue that GitHub may not be a good teacher. Instead, we use active learning to direct human attention to informative and representative examples. Right, so that's all from me. Thank you for your time.
Thank you, Hongjin, for your presentation. Next will be Ken-Wen Peng. Ken-Wen? Ken-Wen?
Yeah.
Are you ready? You can start when you're ready.
Okay, I'm from Race Lab in NC State University. Today I'll present my paper timeline for defect reduction planning. So before that, first I would like to briefly introduce defect prediction. A defect prediction model, as you can see from point 1, is a model that typically extracts static code metrics to train AI models in order to predict bugs in new files from future releases of a software project. So it's a typical binary classification problem. Defect reduction is a little bit different. It's a planning problem that derives from the defect prediction problem. That is to say, after we got the defect prediction model, we ask ourselves, could we further use such information to not only predict bugs, but also generate some kind of guidance to help developers to reduce potential defects? For example, if in some way we can know that a code file is being predicted as defective majorly because one of the code metrics is extremely high, then we could potentially propose a plan to developers to suggest them decrease such code metric using some maybe code refactoring tricks. So therefore, here comes the major question of our paper, that is, how do we generate such suggestions using what kind of knowledge? So we have two important questions we need to answer. That is, first, we need to find out what features contributes most to a defective prediction. In other words, for each prediction outcome, what are the most important features? Secondly, we need to know that among those important features, which of them are actually changeable. So for the first point, if you can see from the pointer on the screen, we use a well-known explanation generation tool named Lime. So it's a local instance-based explanation generation that will inference the prediction model to generate to show users the importance weight of each feature. And you can see that we can, using Lime, we can know for each static code metrics whether their value is positively related or negatively related to the prediction outcome, and how important are them. So that's the first step. Secondly, we want to find out that given this important feature importance of the features, we want to find out that which of them are more changeable. A previous research, if you see point 3, a previous research on actionable analysis shows that different code metrics have quite different change frequency across multiple releases. Therefore, in our case, we also designed our own actionable analysis process. That is, we collect all changes that happened in previous releases, such that when we generate a plan, we will only include patterns that has been seen and recorded in previous releases. And that process is supported by frequent item set mining. So as you can see from point 4, this is basically how timeline works. First, we find out the important features for each prediction. Then we filter out among those important features to find out the actionable patterns that are being recorded in previous releases. And the overlap of these two sets will be the finalized plans generated by timeline to users, so that we can keep features that are not only important but also actionable. As you can see from point 5, we compared our approach against 4 other prior works as well as other baseline methods, and we find out that timeline perform much better than others in terms of similarity and also improvement scores. For the full details of our experiments, please go to the URL shown above for more information. So the general lesson we learned from this case study is that when we attempt to use AI tools such as Lime in SD tasks, we should better first consider how to customize these tools with our domain knowledge. As seen in this paper, with some simple modifications, we can get much better results. Thank you.
Thank you, Ken-Wen, for your presentation. The first 2 papers were from Journal First track. The next one is actually technical paper. Anant? Hi.
Give me a moment here just to share my screen.
You can start when you're ready.
Sure. Can you all see my slides?
Yes, we can see your slide and we can hear you very well.
Perfect. Thank you so much. Well, thanks, everyone. My name is Anant Karkar. I'm an applied scientist in Microsoft's developer division. And today I want to give you a brief synopsis of our recent work on using machine learning to reduce false positives in analytic bug detectors. Now, at a high level, the premise of our work is to try and detect bugs in source code. And this is something that static analysis tools have become quite effective at over the years. Today's static analyzers are able to find many different types of bugs in many different programming languages. One particular analyzer that's quite powerful and that's become quite popular is Infer, which is intended mainly for memory bugs. There's two things that tend to stand out about Infer. The first is that it's interprocedural by design because of the way that it performs its logical analysis. And the second is that Infer supports several different programming languages out of the box. And thanks to the recent Infer Sharp project, it now also supports C#. However, static analyzers in general, including Infer, tend to report a large number of false positive warnings, and this creates a lot of friction with developers. And from our conversations with developers in the field, this is one of the major barriers to these analyzers being adopted more widely across the industry. So we set out to try and solve this problem by creating a machine learning post filter that would classify Infer warnings as either valid or invalid. So given a list of Infer warnings, along with their file and line numbers in the code base, we would decide which of these warnings to keep and which ones to filter out and not present to developers. And for each of these warnings, we would make this decision, or rather the input to our models would be made based on the source code of the repository and the source code of the method where the warnings occur, as well as certain debug information that was outputted by Infer. So we took two high-level approaches to try and solve this problem. Both are based on transformer models. The first was a typical supervised learning approach using a set of Infer warnings that had been hand-labeled as to their validity or not. And for this data, we used a CodeBERTA encoder model. So this is a type of Roberta model, more specifically. And we took this model and pre-trained it on Java and C# methods that were just from open source projects on GitHub. And then we fine-tuned it on our set of hand-labeled Infer warnings in a binary classification task, just to predict those warnings as valid or invalid. The second approach was a little bit unorthodox in comparison, and that was to use a model called GPT-C, which is based on the well-known GPT-2 architecture, which is a decoder model. And GPT-C was pre-trained for line completion. So given a snippet of code and an incomplete line at the end, GPT-C would offer recommendations for how to best complete that line of code given the code before it as context. So the way we use this model is to try and extract signal from the completion recommendations as to whether a given warning is valid or not. I'll illustrate this with an example. For a null reference, if GPT-C recommends a null check in its completions, we would take that as a signal that the null dereference warning could be legitimate because the model is recommending that it should be guarded against. And so because of the way that we use this model, we use it in a zero-shot setting, which means that beyond the pre-training that was done on a variety of different programming languages, we don't have to perform any additional training. We simply have to tune the way that we analyze the outputs of the model. So here's a summary of our results for null dereferences, and these are on Java projects in particular. And we can see that both of our transformer models are able to increase precision beyond baseline Infer by about 15 to 17% relative, while taking a similar reduction in recall. However, we think that this trade-off is favorable because what we've learned from talking to developers and how they use static analyzers is that they tend to favor precision over recall. The reason for this is that if we present a small set of high confidence warnings to developers, it's much more likely that those developers will actually triage, address, and then ultimately patch those warnings in practice, as opposed to if we try to find everything wrong with the project at once and then sort of flood the developers with a large set of warnings. We also wanted to explore how well this post-filter approach generalizes beyond null dereferences to other types of warnings. So we tried to test this on resource leaks. Now, our set of resource leaks was smaller than our null dereferences. So rather than try and train an additional model on this, we simply evaluated our zero-shot GPT-C approach. What we found here is that we were able to increase precision slightly, but with a much larger reduction in recall. So we take this as evidence that it is possible for such a post-filter approach to improve precision on resource leaks in a more viable way with some additional work and some additional development. And finally, in terms of directions that we want to go moving forward and areas that we think would be interesting for further exploration, the first is, of course, to expand this work to additional warning types beyond null dereferences and resource leaks and other programming languages. Another idea is to try and use extended context, to use something like the retro framework that can fetch code snippets from other parts of the code base, and finally to automatically patch bugs instead of just detecting them. Thank you.
Thank you, Anant. Next is a paper from Beijing, Peking University. Fang Liu, you can start when you're ready.
Okay. Hello, everyone. I'm Fang Liu from Peking University. Now I will present our paper, Learning to Recommend Method Names with Global Context. During programming, developers must name variables, functions, etc. However, the appropriateness of a name changes over time during the software evolution. A good function name can degrade into a poor one when the semantics of the function change or the function is used in a new context. Poor names can make programs harder to understand and maintain, leading to misuses and defects. In recent years, researchers have proposed automated approaches for suggesting the method names, for suggesting the consistent and succinct method names, where different model architectures and the method contexts are considered. However, the nested scopes of the project and the documentation of the method are ignored. We first conduct a statistical analysis to explore the relationship between the method names and their contexts by computing the percentage of the token sharing. We can get the conclusion that developers always refer to the project-specific and documentation context when naming the methods, and this context should be carefully considered. Based on the analysis results, we propose a global transformer-based neural model for method name recommendation. This is the overall architecture of our approach. To fully utilize the contextual information of a method, we firstly extract context from 3 different levels, including the local context, project-specific context, and the documentation context. And this figure shows an example of the context for the Java method getElement. And then we build a transformer-based model to generate the method name. Specifically, we build corresponding encoders to encode the context of different levels into vector representations. We also argue that the methods in the project-specific context that are invoked by the target method are more important and relative. So we give these methods more attention by multiplying the invoked with matrix on the hidden vector. And the decoder then generates the target method name by sequentially predicting the subtokens, which uses the attention mechanism to allow the model to attend to different contexts in different decoder layers. Now let's look at the experiment. And we use a benchmark Java dataset to evaluate our model. And here are the parameter configuration and the training details. First, the research question is the comparison against state-of-the-art models. We can find that our model outperforms all the baseline models by a large margin, especially on the exact match accuracy. And the second research question explores the contributions of the context in the same file. And the results show that using different in-file contexts is essential and efficient for improving our model's performance. And in RQ3, we further evaluate the contribution of the cross-file contexts. And the Bayesian study shows the cross-file context is also indispensable for improving our model's performance. And finally, we perform a qualitative analysis to figure out in what cases our model generates different names with human. According to the questionnaire results, we summarize top 4 representative situations. First one is that our model tends to generate a detailed name that contains more information about the method's functionality. And the second cases are that the human written name and our name and the method name generated by our model have almost the same meaning, but they use the synonyms as in subtokens. And the third case is that when some human written names contain an acronym for the specific entities. In these cases, our model cannot correctly infer its correct name. And the last case is that both the human written name and our name can almost have the same meaning, but the subtoken orders are different. And finally, I would like to make a conclusion. We extract a global context which includes the context of different levels, and then we build a new architecture for method naming. And finally, our model gets the state-of-the-art results on Java method name recommendation task. Okay, thank you for your attention.
Thank you, Fang Liu, for your presentation. I know there's a couple of questions already coming up on the chat, but we'll talk more about this later after our presentation is over. Next is Xinyu Gao from Nanjing. Xinyu, you can start presentation when you're ready.
Okay. Hello everyone, my name is Gao Xinyu from Nanjing University in China. Today, I will be briefly introduce our paper, Adaptive Test Selection for Deep Neural Networks. We are entering the area of deep learning. Deep neural networks have been deployed in many fields. DNA-driven software, essentially it's one kind of software program, could also suffer the software defects that may cause huge losses. Therefore, the requirements for quality assurance techniques have become exceedingly demanding. In practice, developers often retrain the DNA model with rich data to fix the incorrect behaviors. They need to collect many data and hire a large workforce to label them. Therefore, identifying and selecting the most representative data become critical. There are two families of test selection techniques: coverage-guided test selection and prioritization test selection. However, both of them have limitations. Therefore, we propose our method ATS. The overview of ATS is as follows. First, for given test inputs, we obtain the output vector of a neural network. Next, we propose a mapping relationship, which converts the output domain into a set of intervals to describe the fault pattern. Finally, we propose a fitness metric and select tests based on fitness value. We use a 5-step process to calculate. In the first step, we cluster the test data based on its prediction category. Next, we construct an index set for each test case in cluster. Each element in set represents a local domain. Step 3 is project operation. We project output vector onto the plane and get the local information by prime. Step 4 is extend operation. In this step, we extend the subspace vector by prime to an interval. As shown in the picture, we determine the intersection point by extending LLY prime to LPLQ. The local fault pattern is designed as a segment GK. The length is determined by the uncertainty. In the last step, we collect all local patterns from each local domain as its fault pattern. Before test selection process, we need to know how to calculate the fault pattern of a test set. For each cluster, we take the union of all corresponding local fault patterns under each local domain. With the help of fault pattern, we propose a fitness metric that assesses the difference between test case and the selected test set. We divided the whole selection procedure in two parts: cluster by cluster selection and total selection. Generally, we select a test case with higher high fitness value in each cluster. If the candidate set is unbalanced, we select the rest part based on the fitness value or uncertainty. We experimented ATS with 4 modules and 4 datasets. The baseline selection methods are divided in 2 types. We choose 4 typical techniques for each type. In RQ1, we compared the average for the detection rate between ATS and baseline methods. The curve-guided test selection methods have a poor performance, while most prioritization methods perform better. ATS had the best result in most combinations. In RQ2, ATS achieved the best result for selecting diverse faults in all combinations, while prioritization methods are sometimes even worse than random. This phenomenon means that, although prioritization methods can sometimes detect more faults, the test cases selected may have an uneven distribution. In RQ3, we evaluated the effectiveness of retraining the DN model with the selected test cases. Only in a few configurations, there are some prioritization methods that show similar performance to ATS. Such results support our assumption that, instead of selecting more faults with less diversity, ATS could select a subset with enough faults with more fault types, which is more effective to enhance the DN model. We summarize the advantages of our method ATS. First, ATS could adaptively determine which test in the candidate set is more suitable to be labeled manually. Next, ATS could select a test with enough and diverse faults. Finally, ATS could optimize the DNN model with a much lower labeling cost. That's all for our presentation. Thank you.
Thank you, Xinyu. Our next and the last presentation will be by Anjiang Wei from Stanford.
Hi, thanks for the introduction. Hi, everyone. I'm Anjiang Wei, and I'm going to present my work on free lunch for testing, fuzzing deep learning libraries from open source. This is joint work done by me and my collaborators, Yinglin, Chenyuan, and Ling Ming. We're from Stanford, Illinois, and Nanjing University. In this work, our fuzzing target is deep learning libraries, that is PyTorch and TensorFlow. Let me start by showing one example bug found in PyTorch by our tool called FreeFuzz. The bug is an interesting one because for the same input, the API torch.nn.maxoutput2d throws an exception on CPU, but passes silently on GPU. After inspection, we find that the exception is actually expected because the input is actually invalid. So GPU produces a wrong result silently without throwing any error. FreeFuzz finds this bug because it applies random test input generation and differential testing. Now you may be wondering this question. How does FreeFuzz know the right types of parameters for invoking this API, maxoutput2d here? How does FreeFuzz generate the code? So this is the challenge of fuzzing APIs because the APIs in DL frameworks are mainly exposed in Python, a dynamically typed language. Therefore, it is hard to determine the parameter types for test input generation. Let's take a look at the conv2d API's definition and PyTorch official documentation. Based on the API definition itself, we can hardly infer type information for its parameters. Luckily, for this widely used API, the documentation provides more information about type. Instead of mining from this natural language description, the way we resolve this challenge is by dynamically tracing the API invocation when running existing code. We record the parameter types and values in the instrumentation, which will guide the fuzzing stage later. Next, I will gradually show the overview of our framework, FreeFuzz. The first stage is code collection. As shown in the figure, FreeFuzz obtains code from 3 different sources. That is, code snippets from library documentation. The second is library developer tests. And the third is various DL models in the wild, all of which can be obtained from open source automatically. The second stage is dynamic tracing with instrumentation. FreeFuzz first hooks the invocation of those APIs and then executes the code collected in the first stage to trace the dynamic execution information for each API invocation. As a result of this second stage, FreeFuzz constructs the type space, API value space, and argument value space for the later fuzzing stage. Then the third stage is mutation-based fuzzing. Basically, FreeFuzz effectively generates mutants for the test input used to invoke the targeted APIs based on the traced information collected in the second stage. The mutation strategies are composed of type mutation, random value mutation, and database value mutation. The last stage is running all the generated tests with oracles. FreeFuzz resolves the oracle problem by differential testing and metamorphic testing on different backends and hardware. FreeFuzz is able to detect various types of bugs, including wrong computation bugs, crash bugs, and even performance bugs. Due to the time limit, I cannot show the details of the instrumentation stage and the mutation rules that we designed. Please refer to our full video and full paper for details. In conclusion, in this work, we propose FreeFuzz, the first general-purpose and fully automated API-level fuzzing for deep learning libraries. The reason why we call it a free lunch for testing is because FreeFuzz mines code snippets from documentation, developer tests, and their models in the wild, which all can be obtained from open source. After that, FreeFuzz mutates the trace input via type mutation and value mutation. It can detect various bugs via differential testing and metamorphic testing. It's worth noting that our idea of fuzzing from mining is generalizable to other domains. So far, FreeFuzz has detected 49 bugs for PyTorch and TensorFlow, with 38 of them already confirmed by developers as previously unknown. FreeFuzz can also cover 9 times more APIs than prior work, with only 3.5 times lower overhead. Our code is publicly available. Thanks for your attention.
Thank you, Anjiang, for your presentation. Okay, good. Now is question and answering sessions, and I see already there's many questions, and some of them are already answered. But I want to make sure that all the questions are answered. Why don't the authors actually come up to the panel, and it's like a panel session, so you can actually take care of those questions. From Lavinia, Hongjin, I think this is for you, right?
Yes, that's right.
Okay.
So, right. So the question is for choosing Java API solution. So actually we chose the Java APIs because that was what the previous work chose. And for a fair comparison, we had to use the same set of APIs. So it makes it clear that the improvements come from our contributions that were built on top of on top of their work. So, but generally, you would expect that a lot of the ideas would generalize to other programming languages as well, because most of the Java features, like essentially the graph captures things like control flow, data flow, return values, what types of exceptions are thrown. So those things would generalize to other languages as well. Yeah, so that's all for the first question, I think. And I wonder if that answers the question.
There is one more, I think, from Fang Niu, right?
Yeah.
To Hongjin.
Yes. Right. So the question is what is the insight of using graphs to represent the APIs instead of other formats such as sequences? Is it common sense in this view? So in fact, it is. There's a long lineage of work, I think, from many years ago, from tools like GroomMiner, right? So that's like 2010, I think. And since then, there's been papers building on top of that and representing code as graphs. So the idea is to combine just not only data flow but control flow and other relationships between program elements into the graph. So I think there's some recurring ideas in the security community as well, because there's early in the 2010s, there was a work called the code property graph, which has very similar motivations, although I think they compose a different set of information into the graph. So using a graph would be better than using a sequence, because it would capture the different multiple execution paths that could be taken in practice, whereas a sequence it will not represent this information explicitly. So I guess that is the main insight of using a graph. You can compose a lot of types of information in it. So I wonder if that answers your questions.
Yes, thank you for answering.
Good, thank you. Next is for Ken-Wen, but I think Ken-Wen already answered the question from Lavinia, right? Yeah. And there is a question for Fang Niu, right? And Fang Niu already answered the question, right?
Yeah.
Okay.
Actually, the question is, are there any plans to compare the structure and different coding conventions of the project? Actually, we do plan to take the coding conventions into consideration when we firstly building the context. However, we find it's hard to define and formalize the coding conventions. So we didn't not yet find a proper way, but we are still very interested in this topic and try to find out the proper way to define and formalize the coding conventions. And maybe future we will take this into our consideration and make a more better model for the method naming.
Okay, good.
So maybe the next question is for me, right? So from
Yes.
Lavinia. So Lavinia asked me, did you face the problem with extracted documentation being outdated or newer functions with low level of documentation? Yeah, that's right. So because we mine we actually find several bugs in the documentation because the actual function signature doesn't match the documentation. We certainly find such kind of bugs, but the approach we adopt here is not mining from the natural language description or the specification from the documentation. We didn't do that. We actually use the existing code examples in the documentation because many APIs, their documentation will have some example code for tutorial. So users typically read those documentation and they will have the examples, and we run that example code for instrumentation. And but many APIs are missing such documentations, are missing such tutorial code. So we also run the developer tests and also many open deep learning models in the wild to make a complement. So to complement our approach. I think does this answer your question? Actually, I have another question for Anant about machine learning for static bucket detectors. So I think this work is very interesting, and but now I think your machine learning algorithm finally will give whether the warning is valid or invalid. But I think a better way might be to rank those warnings, because so from my understanding, those static analyzer will do some approximation when analyzing the code statically. If there is more approximation that happens during the analyzing phase, then you may want to rank them lower as low priority. If there is less precision, there is more precision, then you want to rank them higher. Right? So what do you think of this idea?
Yeah, it's a great point. And actually, we took some of these models and worked with one of our internal teams at Microsoft and sort of went through the experience of them actually using the models. And the way we used them in practice was actually just to take the info warnings and re-rank them using the confidence scores from the outputs of our models. So in practice, we think that's probably the best way to use these models for a team that is actually running Infer. The advantage of using the machine learning models as a post filter is that it allows us to get confidence scores on all the different Infer warnings. When Infer outputs an analysis, it just gives us a list of warnings and metadata about them, but it doesn't return any kind of confidence score. So one of the benefits of the post filter is that it lets us assign confidence scores to the models for the purposes of re-ranking. But at a high level, yeah, you kind of hit the nail on the head that the sort of best way to use these sorts of models in practice is to use them for ranking.
Yeah, thanks. Thanks for the answer.
Mm-hmm.
Yeah, I still have a question for Anant. Yeah, I'm wondering if you just try to find whether there is a bug, or also can figure out where the bug is.
Sorry, I think I missed the question. Could you repeat that? Sorry.
Yeah. Is your tool just try to find out whether the code has a bug, or can also locate the bug where the bug is?
Yeah,
Just,
that's a good question. So what we found from previous works to try and sort of use machine learning to detect bugs in the wild, the way you'd use a static analyzer, right, is you would just sort of let it loose on a code base. It would perform its analysis and then return to you, bugs in specific locations. What we found is that if we try to mimic the same process using a machine learning model, like even something like a transformer, it tends not to work very well because these models tend to perform poorly when it comes to localizing bugs. So when it comes time to, given a large code base, identify specific points in those code bases where different types of bugs happen, trying to apply machine learning at that scale, a machine learning model at that scale tends not to work very well. So that's the reason why we actually turn to static analysis, and the reason why we frame the problem as a post-filtering problem is we let the static analyzer do the localizing for us, and then we just have to make a decision on each warning as to whether it's good or bad. So the bug localization aspect of it is something that static analyzers have actually done quite well. And we found that when we tried to replace them with a machine learning model, it didn't work very well in practice.
Maybe can you just use, I guess, maybe can you just use the attention weight to perform analysis for locating the bug? Since it can perfectly predict whether the code has a bug, maybe I guess the network may also can have the ability to locate the bug, the location.
So one thing we're looking into in that regard is ways to essentially take transformer models and apply them to larger bits of context. Usually, given the length of the input that these models can take, it's generally limited to about one method or maybe a handful of methods. So one of the things we're trying to look at is, and sort of like I alluded to, when I was talking about retrieval augmentation, is ways to allow these models to reason over large pieces of the code base, as opposed to just a short snippet of code like a method. Because then when you compare something like that to an inner procedural analyzer like Infer, Infer is able to analyze an entire call stack worth of methods. Whereas if you try to replicate that process, even with the attention weights of a large transformer, it's much smaller. It's limited to a very finite amount of code. So the principle of what you described of trying to use the attention weights is definitely something that we're actually hoping to work more on in the future. We'd like to be able to use the powerful transformer attention to just reason over the code directly, but we think that allowing it to expand into bigger context is something that'll help us get there.
Okay, thank you.
I have a question for Xinyu. So Xinyu, in your adaptive test selection for deep neural network, I'm wondering the further implication of your work. So if you can select the text very fast and you can, if it demonstrates that the deep neural network is not doing good, then what will happen? So after you do the test selection, what's the next step? Do you want to retrain your model? Right.
Yeah.
So what's the next step of your work after applying your technique?
Here is the roadmap of my technique ATS, and as you see, first we collect many massive and label data, and we use our method or other test selection method. We can select representative data. We can select a small portion representative data from a large massive and label data, and then we label them and use this data to test and retrain the model to fix the incorrect behaviors or get a good performance. And our method can adaptively select more and diverse faults. In this step, we first compute. We first propose a mapping relationship to convert the output domain to a fault pattern. Then we propose a fitness metric, and use this metric, we can ATS can guide the test selection process. Our work is the first adaptive test selection method for the deep neural networks. Is that okay?
No, you don't answer my question. So my question is, after you find some test input which can indicate the fault in the deep neural network, what's your next plan? So what's the next step? Should I retrain the model? Or you said
Yes.
you want to fix the fault. How to fix the fault? It is an unknown problem. It's because the only way to fix a neural network is to retrain the model, right? Is this what you mean? You want to retrain your model?
Let me see. In the existing work, the developers often retrain the model to fix the incorrect behaviors. And the process is we find the data, and the data reflect the incorrect behaviors of the model. And because the DN model employ a data programming paradigm that we cannot tuning the pattern by tuning the parameters manually. So we employ we can use we can collect data and use data to fix the incorrect behaviors such as retraining. As far as I know, there are few work focus on other methods. Most in the existing works, most of researchers use the retraining to fix the incorrect behaviors, such as improve the model robustness, and improve the model generalization. As far as I know, I also know there are few works to change and change the DNA article to get a good performance, or improve the model accuracy. But the most of existing works in the software testing use retraining to fix the model, fix and training the model. And we assumption that we can collect data, and use the data can fix the incorrect behaviors.
Yes, thanks for the answer. Yes, it makes sense to me.
Yes.
Okay, there is a
Thank you for the
question from Hongjin to Anant on the chat.
Yeah, I think it'll be easier to just talk through the answer than try and type it in the chat. So the question was how much subjectivity was there in labeling the warnings in the data set, and how much effort did it take for developers to try and label them? The short answer is it's quite expensive to have developers actually hand label these warnings. And as you can imagine, even for the data sets that we worked with for training these models, we were dealing with data on the scale of a few hundred warnings. And so it's good that we sort of had pre-trained transformers to work with, that we only had to fine tune on this data. But it is in general quite expensive. As far as the subjectivity, one of the things we tried to do to limit that was to find the original developers of the code that we were analyzing. So if we took a particular project, ran infer on it, and it generated a list of warnings, as often as we were able to, we would try to take those warnings and go back to the original developers and then ask them to sort of triage some of the warnings, because they're of course the ones who know that code base the best because they're the original developers. So that was one of the ways we tried to eliminate subjectivity. And like I said, in general, even if it's the original developers, it's still an expensive process.
Right. Do you have any estimates on the amount of time they took to label one warning?
To label one warning, I don't think I have like a concrete time estimate. I would, if I had to sort of, give like a ballpark number, I would say it was on the order of, several minutes per warning. Potentially, some of them with a large degree of variability, of course. Some warnings you could look at and make a decision in a matter of 30 seconds. There were others that required a much deeper dive into the source code and required a lot more investigation to figure out if the warning was legitimate or not.
Right, I see. That
Because analysis is interprocedural, making a decision sometimes meant you had to look at 5 or 6 methods.
Yeah, that was I had the same experience as well, because I had another ICSI paper where I labeled false alarms of like static analysis warnings, and we had the difficulty in constructing a data set and like labeling them, because there's a lot of subjectivity, and in many cases we couldn't say whether it was a true alarm or a false alarm.
Yeah, that's definitely one of the issues. And the other side of that coin, to try and run something like Infer or any static analyzer on a very large corpus of code, and then try and use some sort of heuristic to identify the false positives, that tends to be a very noisy process, and so you end up with a different set of challenges. So, yeah.
Yeah, thank you.
Mm-hmm.
Okay, any other questions? I have a question for Fang Niu. Actually, humans are much better in abstraction, right? So, have you thought about how your approach could be, enhanced in the future to consider such abstraction in discovering the name entities?
You are unmuted. You should first unmute yourself.
Fang Niu, you're
Okay, sorry.
Yeah.
Yeah, I think for the machine learning based approaches, such as or including the deep learning neural networks, I think the data set may be is the most important thing. I think in existing data set, benchmark data set, although they are collected from the top ranked repositories, but still have some the names are still not very good as we expected. So I think maybe we can future build a more realistic data set, such as make some filtering about the quality of the names, so that our model can be learned in a better way. That's such as has the ability to perform much like more like human, and maybe have the ability of abstractive.
Thank you, Fang Niu.
Thank you.
There's one question on the chat from Hao Li to Anjiang.
Yes, so FreeFast based on data from different sources seems like FreeFast understand the interface better than the documentation. For instance, I'm wondering if it's possible to use the information to enhance existing documentation. That's an interesting idea, but actually FreeFast understand the interfaces better than the documentation. Yeah, so sometimes we find that because we instrument the APIs, and sometimes we find code that can, because some parameters allow multiple types in Python, because Python is a dynamic type language. Some parameter can support can have receive integers or a tuple of integers, and if the documentation can be wrong, because sometimes documentation it must be an integer, but actually it can be either an integer or a tuple of 2 integers. So in this case, if things like that happen, then FreeFast will be able to find documentation bugs and fix them. Yes, I agree. But we may need more experiments to demonstrate that idea actually, works. We need more experiments to do that. Yeah, thanks for the great question, Holly.
Great, thank you. Actually, 1 minute left, or even less. I think that was. If there's any quick question, I think we can handle here. Otherwise, we need to wrap up. Okay. It was a great presentation and also great question answering sessions. If you have any further questions, I think you can find